And here we go for Chapter 7, Section 2, Climate. All right, once again, weather, largely what's happening right now. Climate, what I expect to be happening, because it's what's occurred for 30, 50, 70, 80 years in this area. If somebody is coming to Florida in July, it's going to be hot. Be prepared for it. Somebody's coming to Gainesville in December, bring everything. It might be cold. It could possibly get near freezing. It could also be 80 degrees out there. You know, what we expect. You're going to visit Arizona, I expect it to be hot and dry. You're going to go visit New York, I sort of expect it to be cold, but in the summer, maybe not. So we look at what is occurring. There are several key factors that really determine an area's climate. Why does this area have a climate? Once again, in the tropical areas, you could have rainforest, you could have savanna, you could have desert. You get in the temperate areas where it's hot and cold. Think typical 4 seasons. If we just walk right across the United States, you have forest, you have grassland, you have desert, then you have mountain, alpine areas, and we even have temperate rainforest. So we go from deciduous forest to temperate rainforest to grasslands, to all in the same sort of swath. So what are the big key factors? It comes down to these 5. Incoming solar energy, the rotation of the Earth, global patterns of both air and water, atmospheric gases like greenhouse gases, and the Earth's surface features, most notably mountains. So let's walk through each of these in turn and see how they affect weather in general, which drives what our climates are in these particular areas. So on the map up here, they've kind of got it color coded, and there are certain areas when we talk about climates that they tend to be certain ways. Now I'm going to start at the very top up at the Arctic and just work my way down, if you will. So the very top where it's white, that's just ice. This is polar ice. It stays ice, snow on it virtually year round. And then we move down and we get into these subarctic areas, our tundra and taiga. Tundra is a little bit more grasslandy, taiga is a little more foresty, but they're continually cold climates. Then we move into this kind of darker green. These are our cool temperate areas. This is where we do get some actual temperate rainforest, but a lot of these tend to be foresty. The purple coloring is highlands. This tend to be some mountainous areas. We look at the orange. These are warm temperate environments. This hits where we are here in Florida, etc. The yellow tends to be areas that are very dry, and we'll look at some reasons why we find them in these specific spots, because there's a good reason why we see desert right in our Midwest. We see desert in Africa right on the 30th parallel pretty much, and up through other areas and also down in Australia. And then in blue, it's highlighting at the ocean. These are some of the major upwelling zones where water is pushing upwards, and this helps drive currents. It shows a lot of the other currents, etc. That's a nice, neat map of just where some of these different climate zones tend to be. Now, weather on those on any given day could be different, but this is climate, what we expect to happen. Let's look at these factors that determine these overall regional climates. Bring the picture up here. There's a lot going on in this picture, but let's focus on a couple of things in general. We tend to get this cyclical movement of air, which is driven by solar energy and convection currents. Now remember, hot air rises. So as the sun comes out, hits the ground begins to warm up, the air sitting on the ground gets warm, and that air begins to rise. So more air, so I get this rising air current, and as that air current rises, it cools off, and eventually it falls, and as it falls down, it gets sucked back in, and I get this big current. On that side where you see these kind of orange and red ones, that's what they're trying to show. They're trying to show these convection currents. Where the hot air rises, it cools off. So what happens is it tends to rise up here and it goes both ways. Now these happen in really big ones right along the equator. So if you'll give me a second here, I'm going to grab my globe. Be right back. All right, so with the globe, the equator is running like right through here, and right around here is our 30th parallel. So what happens is, this is the hottest area, so the hot air rises, and it rises, it begins to cool off, and it tends to fall in this area. So I get a big convection current here, and it's happening the same thing here. It's rising, cooling, and sinking. So I get right over here these big convection currents, and then it occurs here as well. That's what we're looking at, this area. As the sun is hitting it, we get these convection currents. So what we would expect is the wind just to blow from where we are in Florida. If the wind's coming up and it's falling right here, we would expect to get north to south winds all the time because the air is falling and getting sucked in, but the earth is spinning. So because of the spin of the earth, we get the Coriolis effect. Because as the air is rising, when it's falling, it's not falling at the same place because the earth is spinning. So when we talk about planet Earth, it's this rising of air, falling of air, and the spinning of the earth that gives our large overall wind patterns. And these are what we call our trade winds. This came from the days of the ships trading. They would follow the currents. They would go down and follow the trade. If they tried to sail straight across, it was difficult. So they just followed the wind patterns, and it made a complete cycle. They would take goods down to here, trade something off, load up the ship, sail over to here, sail up into North America, sail back over to Europe, and they just did these big circular routes, referred to them as the trade winds because they worked their trade from it. Also, we will talk about insolation. Insolation, not insulation like what you find in your ceilings and walls, insolation. This is the amount of solar radiation reaching an area, and it varies by latitude. So, let's take a look with this. Now, it may not be real easy to see, but if I am at the equator, the sunlight shines and hits it pretty directly. So I get something akin to a circle of light. So all my sunlight is very direct, but when it hits up here, it spreads out. So I go from having a nice round shape to having a ovally shape. Now it's the same amount of energy coming out of my flashlight, either making a circle or an oval, depending on where it hits. So if it's getting a circle of light near the equator, or when the sun is tilted towards us, we get direct light, so it's summer. But when the earth tilts away, the light hits a larger area and we get less radiation. So if it's a circular light, we get all of the energy hitting this area. But if it's an oval of light, it's a larger area of space, and the same amount of energy is hitting a larger area of the planet, so you get less solar radiation per square kilometer in the oval shape than you do the circular shape. So this uneven heating of the Earth's surface is what causes some of these climates. So in the picture we have here, it's showing that to a degree. The air heats up and it rises. Well, as that warm, moist air is rising, it cools off and it rains. So right around the equator, we tend to have areas with high amounts of rain because that warm, moist air is rising, and we tend to get our tropical rainforests there. But as we move inland, and somewhere like Africa, you get away from the coastline, and the moisture's already dropped, so that's where we may move into our savannas. But as this warm, moist air, it rains. As it gets high and cold, it's lost all of its air. So where it falls, that's where we get our high pressure systems. So it's this condensed air and it moves over. We have this cool, dry air. And as it comes down, it warms up, because we're up there, it's dense and cold, and as it falls it begins to warm up, but it doesn't have any moisture in it. It warms up now, but it's warm and dry, and this is our high pressure system. So we get these big cycles. So where that air is falling, this is where we tend to get deserts. That's where we find our Sahara Desert. That's where we find desert in Australia. It's around this, near this 30th parallel, where that air that all the moisture is out of, it's cool, but as it falls, it begins to warm up. This creates our high pressure, and we tend to find deserts in these areas. So that's one of the reasons. Another is the tilt of the earth. Once again, I'm going to point to us here in Florida. The earth is tilted at about a 20 degrees. If you at the camera represent the sun, if it's summertime, we're tilted toward. So we're getting direct sunlight, or if you will, we're getting that round sunlight hitting us. And then as the earth goes around the sun, well, we're tilted this way, but as we go around the sun, well, when I get back on this side of the sun, we're tilted this way. So now we're tilted away from the sun, so we get the oval of light hitting us. If we're tilted towards it, it's this way. If we're tilted away. So this is what causes our seasons. If we're tilted towards the sun, we get direct sunlight, more insolation, and it's warmer. If we're tilted away from the sun, then the sunlight is glancing off of us a bit, and we don't get as much radiation, and it's overall cooler. So if it's summer for us, well, it's winter for Australia. If it's winter for us, it's summer for Australia. The equator doesn't change much because they tend to get a lot of insular radiation no matter what they are because of their orientation. But this tilt affects us as well. So the farther away you are from the equator, it's cold all the time, cold all the time, warm all the time. So we get tropical regions between 0 and 30. We get polar from 90 to 60, and we get temperate from 30 to 60. So from 30 to 60 is where we get our classic 4 seasons, if you will. We can have extreme temperatures here, and anything living there has to adapt to being freezing cold part of the year and really hot part of the year. So these are our big, large bands. And why? And that's because of the tilt of the earth, typically. The ocean currents that we have up here distribute the heat. Sun comes in, it warms up the planet wherever it's hitting. And we get some different, it's warmer at the equator, typically colder at the poles. Well, as the ocean also does the same thing as the air. Hot water rises, cold water sinks. So at the poles, the water tends to sink and move towards the equator. It gets warm and rises at the equator, and we get these large currents that are redistributing it. The red lines are showing the warm, less salty, shallow currents. So these are the currents staying closer to the surface. The blue are the very deep currents. These tend to be colder and saltier. The more salt in water, the denser the water. So if water is cold and salty, it's denser, and that's what we tend to find down at the bottom, and they follow along in these currents. And from that other picture, we saw there are certain areas where there's upwellings, but these tend to help drive our main climates, because if you live near the ocean is warm and it carries warm water with it, and it keeps areas near the coastline a little more milder or temperate than somewhere that's inland and they don't get the benefit of warmth from the ocean. Let's talk about greenhouse gases along with climate. Now, we all hear about global warming and greenhouse gases, and we go, oh no, that's all bad. Now, bear with me here. Global warming is a good thing, because without it, we would be a frozen wasteland. we would be about 0 degrees Fahrenheit or about -18 Celsius if it wasn't for the greenhouse gases. But my mom was famous for her saying, too much of a good thing, can be a bad thing. We need the greenhouse gas to be warm enough, but if we have too much of it, we don't want to be too warm because that's what's driving climate change. And as things change, it's a disruption. Now, you're not with me on this global warming thing. Well, let's think about the moon. Does the moon have water on it? Yes, it does. Not liquid water, but it has solid water, ice. Is the moon any closer to the sun or farther away from the sun than the Earth is? Depends, right? Because it's orbiting us. So sometimes it's closer to the sun and other times it's a little farther away. But even when it's closer to the sun, it doesn't have liquid water on it. Why? No greenhouse gases. Nothing to re-radiate the sun's heat back onto the moon to keep it warm enough. So our atmosphere acts as a little shield. And the atmosphere, the gases in the atmosphere, as the sunlight comes in, warms up the ground, it hits some of these gases that hold on to the heat, and then when the sun goes away, it re-radiates the heat back into the planet, keeping us warmer than we really should be for where we are away from the sun. The global warming or the greenhouse effect is what keeps us alive. So the greenhouse effect in general, good thing, but we don't want too much of a good thing. Let's look at the main greenhouse gases. The main one, the one that does the most effect over the planet of the Earth is water, H2O. Yeah, I know, you're expecting to hear carbon dioxide. That's the one we talk about. But the water cycle doing its thing, evaporating water, the clouds, there's a lot of water vapor. There can be anywhere from like 1 to 4% of the atmosphere can actually be water vapor. Carbon dioxide, the next most important, is only about 0.03%. Water can be 4%, carbon dioxide 0.03%. A very small percentage compared to water. The thing is, humans don't do a lot to really affect water vapor in the air. The water cycle's doing its thing with that. Nothing we've done has really affected it much. So water is the most important one. However, we talk about carbon dioxide because that is the one you and I are having a big effect. Whenever we burn fossil fuels or whenever we burn anything, trees, grass, etc., it releases carbon dioxide into the air. So water is the most important one, followed by carbon dioxide, followed by methane, and followed by nitric oxide. Of the four, 3 of them, humans are largely responsible for causing larger amounts than we've ever seen in our history before. We affect carbon dioxide when we burn fossil fuels or we burn anything. We affect methane by fossil fuels. We find it in natural gas and burning natural gas and releasing it. And also in nitrous oxide, we tend to get a lot of nitrous oxides when we burn gasoline, we burn oil. Coal, we tend to get more of some other things. These are big greenhouse gases. They've always been in the air, and that's why our planet is warm enough to live with. We have the natural greenhouse effect, which is keeping the Earth habitable, and then we have the human-enhanced global warming. The greenhouse effect, normal, natural thing. When we tend to talk about global warming, we're talking about how humans are adding more of these gases into the atmosphere than we ever have before, and it's causing the planet to warm up more than usual, affecting our climate change. Some areas are getting more rain where they didn't used to get it. Other areas are not getting as much rain. Some areas are now warmer. Spring is coming sooner and summer's staying longer. It's a change, and change just can have an effect. The last thing we're going to talk about are surface features. And the biggest surface feature that tends to have an effect on climate, once again, we're talking about large overarching, are mountains. And we tend to get something that we call as the rain shadow effect. And we'll put our picture of it up here. What happens as we have moisture moving in, we have warm, moist air coming in, and as it hits the mountains, it begins to push up because more wind's coming behind it, and it pushes this massive wind air up the mountain. As warm air rises, it cools, it condenses. So as it moves up the mountain, it's condensing, it's getting colder and colder, and as it condenses, it reaches the dew point and it begins to rain. So it begins to rain on this windward side of the mountain because the wind's coming here, it's coming up the mountain, and we tend to get a lot of rain. As the clouds clear the mountain, they get in the shadow of the mountain. We call it the rain shadow effect. So the rain falls on the windward side, and on the leeward side of the mountain, the air descends, but it doesn't have any moisture left in it. So what I tend to get in an area with high mountains, now really low mountains don't cause this very much, like in the Appalachians. We don't see this effect as great because they're very low mountains. But in America, on the West Coast, where we have the Olympic and the Rockies, the Sierras, we do see this. The warm, moist air comes in, pushes up of them, it rains and falls off. So in Oregon, we tend to think of Oregon as this real rainy area, and in Seattle, certain areas it is. But a lot of Oregon is actually high desert because you get on the other side of the mountains and there's no rain left. We call this a rain shadow. And we see it all over. In the Gobi Desert, the wind pushes up over the Himalayas, so it's rainy on Nepal and India side, but Tibet and that area doesn't get much rain. We see it in America. The winds come from the Pacific Northwest, it hits the desert on the other, hits the mountains on the other side of the mountains, Arizona, Nevada, etc., desert. So these mountains play a big feature in where we tend to find deserts a lot of times. If the mountains weren't there, it wouldn't be desert. It might be grassland, depending on how far in it goes. But windward, we get rain. Leeward side, desert, typically. Also, cities themselves create these little microclimates. Asphalt, especially things like our roads and the black asphalt make parking lots out of. These hold and retain more heat than trees and grass. So the sun comes out, warms these things up, and you know this. If you've ever walked barefoot across a parking lot on an August day, you're like, ooh, ah, ah, you're doing the hot dance. It gets a lot more heat. So when the sun goes down, it re-radiates that heat back into the atmosphere. Kind of like the greenhouse gases, but it's what we build in the cities. The cities tend to create their own little microclimates. It tends to be warmer in a city area than the surrounding countryside, and we call these heat islands. And this effect we see over and over. The city area will be a couple of degrees warmer than the surrounding countryside. So cities themselves can actually affect the climate to a degree. Well, that is it for climate, the major things that drive and push what our climates are. Come back next time and we'll look at biomes. Specifically, we're going to look at terrestrial biomes, but how these climates drive our 7 or 8 different biomes. Take care. We'll see you next time.